This is part 3 of the series Relationships Within Triangles, and we're going to start out this part with the idea of a centroid. Now, before we discuss what centroids are inside of a triangle, we're going to need to talk about a median. Now, the median of a triangle is a segment that goes from a vertex to the midpoint of the opposite side. So BE here is a median because it goes from vertex B to the midpoint of AC. CD is a median because D is the midpoint of AB, and so that's a median, and that's a median. AF goes to the midpoint of BC. Now, the idea behind the centroid is the point of concurrency of the medians of the triangle. Now, this is also known as, in physics circles, it's known as the center of mass. And it's really kind of interesting to see, I can't demonstrate it obviously here, but I will in class, that if you actually took a triangle and I made one out of cardboard, and you actually cut out the triangle as cleanly as possible and measure out the midpoints of each one of the sides, if you're accurate enough to form the centroid, you can actually balance that cardboard triangle on that point. And it works out pretty good. It's actually a pretty interesting little experiment to try out. So the centroid theorem tells us that the centroid of a triangle is 2/3 the distance from each vertex to the midpoint of the opposite side. So to put that in perspective here, let's take a look at median BE. The segment BG is 2/3 of the length of BE, making GE 1/3 the length of BE. It also means that BG is twice the length of GE. So once again, segment BG is 2/3 of the length of BE. And so that relationship works for any of the medians. So CG is 2/3 of CD, and AG is 2/3 of AF. And we're going to use those ideas to solve our problems. So remember, you can see, I think, fairly clearly, I don't like to do this often because pictures can be very, very deceiving, and our primary rule is never trust the picture. But in this example, you can see that this piece looks bigger than this piece. And when we're dealing with centroids, you can pretty much always rely on that thing because there's no real way in 3 dimensions to draw a centroid so that it appears differently. So again, 2/3 of the whole, 2/3 of the whole, 2/3 of the whole. Let's see if we can work an example now. In this example, we're told that point Q is the centroid of this triangle, and they give us the length of SQ, the length of the biggest piece of that median. So we're looking to find QW, the shorter piece, and SW, the whole thing. To start with, I'm just going to use our centroid theorem to find our values. So we know that SQ is 2/3 of SW. And since SQ is 8, that's 2/3 of SW. If we solve for SW, just multiply by 3, so 24 equals 2 SW. Divide by 2, 12 equals SW. And since SW is 12 and SQ is 8, clearly then you can see that QW has to equal 4. Another way to look at this problem is to see that this piece being 2/3 of the whole and this being 1/3 is that SQ is made up of 2 of 3 equal parts. So if 8 is made up of 2 equal parts, then clearly both parts have to be equal to 4. So there's a 4 and a 4. And if QW is one of those equal parts, then QW has to be 4. So it's a non-analytical way to do it, in other words, a non-algebraic way, but it still gets you to the same thing. So noticing that this is 2 of 3 equal parts, then we can get to the same result that QW is 4 and SQ is 2 of these QWs, which makes it 8. So either way you want to work these problems is fine. The second way I did works well when these numbers are even. They're not always going to be even. This analytical method always works, no matter what the results are. So my suggestion is understand both and use whichever one pleases you. So let's move on to the next example. In this example, we're given a triangle and we're told to find the coordinates of the centroid of the triangle. So there's a couple of ways we could do this, but the first way is we're going to need to find the midpoints of these segments, because we can make some underlying assumptions, but it isn't terribly obvious that they're going to work quite right. So I'm going to assume that you don't see the easy way to do this, and we're going to work it the longer way around and then back analyze it to look at the easier way to do it. So first thing, let's find the midpoint of ST. 5 plus 8 over 2 and 8 plus 3 over 2, which is 13 halves and 11 halves, which comes out to about 6.5 and 5.5. Very, very ugly. So 6.5 and 5.5 is just about there. So this one's not going to be terribly pretty, but this one's going to be 6.5, 5.5. All right. Now we're going to do RT. So RT is going to be 2 plus 8 over 2 and 1 plus 3 over 2. This one looks a little cleaner. 2 plus 8 is 10 divided by 2 is 5. And 1 plus 3 is 4 divided by 2 is 2. So that's 5, 2. So that's this point. 5, 2. Now let's go ahead and draw the medians in here. So this median is going to go like that, and this median will go like that. And so you can see that this point looks like it's going to be 5, 4-ish is going to be where our centroid is. But we're just eyeballing it, and that's really not good enough. Now what you could do to find the exact value is actually find the equation of this line, and using the equation of this line, find out where these two lines intersect. Now that's certainly one way to do that. If we don't have to do that, it would probably be preferable not to, because it's going to take us a little bit longer. Now, because this is a vertical line, that presents a much easier approach to this problem. But you still have to know the details of where the centroid is. And the reason that this makes it easier is because we just take a look at the length of this line. It's 8 minus 2, which is 6. So this line is 6 units long. And we know the centroid is 2/3 of the way down. In other words, this segment is 2/3 of this whole median. So that's all we really have to do is take the length of the segment, which is 6, and multiply it by 2/3. Because we know that this piece is 2/3 of the overall. Well, 6 divided by 3 is 2, and 2 times 2 is 4. So this gives us 4. So that means this length is 4 units long. And since this piece is starting at 5/8, that's all we have to do is count down 4 units. So from 8 minus 4 is in fact 4. So we know that is our point, and its coordinates are 5, 4. Now, as a purely academic exercise, I'm going to go ahead and show you the harder way and show you that it works out the same way. So to find the equation of this line, I need to find the slope of the line. So the difference of the y's is 11 halves minus 1 over 13 halves minus 2. So 11 halves minus 2 halves is 9 halves, and 13 halves minus 4 halves is 9 halves. These are equal. 9 halves divided by 9 halves, of course, is just 1. So the slope of the line is 1. That's kind of convenient. So using point slope, and we'll use this point because it's much cleaner than that one, we have y minus y1 equals m, which is just 1 so we don't write it, times x minus x1. So there's point slope. Y equals x, adding the 1, negative 1. So y equals x minus 1. Now we know that the x-coordinate has to be 5 because this vertical line is where this point has to intersect. So we know the x is 5. So y equals 5 minus 1, which is 4. And so clearly our y-coordinate is 4. So we know our x-coordinate is 5 and our y-coordinate is 4. So we've confirmed our result. Let's go ahead and move on to the last of the 4 points of concurrency. This point of concurrency is called the orthocenter. The orthocenter is the point of concurrency of the altitudes of a triangle. And the altitude is a segment from a vertex perpendicular to an opposite side. So AF, AE, and BG are all altitudes, even though it doesn't show that they're perpendicular. Now it's important to note that point D, the orthocenter of this triangle, is inside, but that's not always going to be the case. Especially in obtuse triangles, the orthocenter could be outside. But the important thing to note is it's where all the altitudes intersect. So let's see if we can find an orthocenter of a triangle. So here we have a triangle with these given vertices. And the first altitude is an easy one because it's a vertical line going from this vertex straight down. So we're going to use that one. And to find where these intersect, let's look at this altitude. In order to find this altitude, we're going to have to find the slope of this line. Then we're going to have to find what's the slope of a line perpendicular to it, find the equation of this line, and where that line intersects this altitude. And that's going to give us our orthocenter. So to cut time, I've gone ahead and done the work, so let's go ahead and work through this. So we first want the slope of yz. So it's 4 minus a negative 1, that's the difference of the y's, negative 2 minus 3, difference of the x's, which is 5 over negative 5, which is negative 1. So the slope is negative 1. So the slope of a line perpendicular to this, which the altitude from this point to this line has to be perpendicular to this, it's going to be a 1. So let's use our point slope form, and this point, we want the equation of a line through this point perpendicular to this line. So it's y minus negative 1, which is y plus 1, equals x plus 5, or x minus a negative 5. So there's our equation. We subtract the 1 from both sides, we get y equals x plus 4. And when we take this x-coordinate, which is negative 2, and we substitute it in for this x-coordinate, because this line and this line have to intersect, negative 2 plus 4 is 2. So our y-coordinate is 2. Therefore, since the x-coordinate is negative 2 and the y-coordinate is 2, negative 2, 2 is our target point. And so we can see this altitude and this altitude intersect at that point. This line has a positive 1 slope. This line had a negative 1 slope, so these are perpendicular. So let's move on to the next section.